Hey everyone! I'm very happy to meet you virtually at APSIPA this year. My name is Jiahong Zhao, a PhD candidate and Associate Research Fellow at the University of Wollongong, Australia. Before presenting my work today, I'd invite you to answer a question. Is there anyone who hasn't used the video conferencing software, such as Zoom, Webex, or Tencent Meeting? You can type your answer in the chat. Yes or no? Okay, I guess the answer is no, as the world has moved to virtual workplaces. Another quick question. When having a virtual meeting, are your surroundings always quiet? For me, the answer is no. Once I had a regular meeting with my supervisor, I was excitingly talking about my recent research. And then, the following sound joined the meeting. Well, sometimes it was not the drill. It was the train, the pet, or maybe the kids. Not only for video conferencing, many other cutting-edge technologies nowadays need to record a variety of sounds, including smart home products, robots, and autonomous vehicles. These techniques are crucial for people's smart lives, and by achieving a good quality of sound recording, they can talk to people, serve the people, and bring a smart future to people. However, there are always noise, room reverberation, and other interfering sounds in the real world, which can confuse the above products and flood the desired sound. Existing research uses an array of microphones to deal with such interferences and obtain clear recordings by selecting sounds only from the desired direction. But conventional microphone arrays are usually uniformly spaced, which has limited capability of suppressing interferences and recording high-frequency signals. According to the fundamental spatial Nyquist sampling theorem, the inter-microphone distance should be smaller than half of the signal wavelength, which is a well-known threshold to achieve a clear recording. The frequency corresponding to the threshold wavelength is called the operating frequency. If the frequency of the recorded signal is higher than the operating frequency, the recording suffers from the spatial aliasing problem, which means the microphone array cannot distinguish the desired direction and is confused by a few interfering directions, as you can see in the beam pattern in the right-hand side. Coprime arrays have been proposed to address the spatial aliasing problem by changing the microphones to a non-uniform array. The confusing amplification at interfering directions is removed, and the Coprime microphone array amplifies sound mainly from one desired direction. The Coprime array interleaves two uniform subarrays, which can use 8 microphones to obtain equivalent performance of a 20 microphone uniform array. Its general structure can be seen in this slide, in which you can find that the number of microphones and the inter-element spacing are both coprime related. For example, M and N are coprime numbers, and there is only one common number that can divide both, which is 1. The semi-coprime array adjusts the coprime array structure a little and adds a short subarray for further suppressing interferences. Its improved beam pattern and the DOA estimation performance has been investigated in our previous work in APSIPA 2019. The aforementioned two coprime microphone arrays have been applied to beamforming and DOA estimation in existing work, and obtained improved performance compared with the uniform microphone array. But so far, is the potential of coprime microphone arrays fully explored? Motivated by this question, our work in APSIPA this year re-examines the coprime microphone arrays starting from their signal model. As you can see in this slide, we use Y to represent the recorded signal at each microphone. And there are 3 sources in this example, from S1 to S3. All setups are within a room, and the interferences considered include additive noise, room reverberation, and other interfering sources. The coprime arrays need a processor to calculate the outputs of all subarrays for obtaining an overall output. The commonly used one is the product processor, which calculates the multiplication of all subarray outputs. The operating frequency is also formulated for both the CPMA and the SCPMA, which depends on the array aperture, Coprime parameters, and the speed of sound. The speech signal is recorded in this work, which is broadband and can test the array performance for signals both above and below the operating frequency. This work estimates the DOA for performance evaluation. Existing work utilizes SRP-PHAT for DOA estimation using Coprime microphone arrays, which calculates the cross-correlation in the frequency domain first, before considering the influence of its amplitude and maintaining its phase information, resulting in the GCC-PHAT. Note that the GCC-PHAT is calculated for all microphone pairs, which are selected following the process in this slide. This is true for conventional uniform arrays, but is it the best way for subarray-based Coprime arrays? Okay, let's take one step back. As we already know that the Coprime arrays have two or more subarrays and use a processor to combine the subarray outputs, it doesn't quite make sense to select microphone pairs in the same subarray. Alternatively, this work considers all microphone pairs from different subarrays, which means different orientations of the triangles in this slide. The selection process is demonstrated here. The resulting equations of the total number of microphone pairs for the two Coprime arrays are also given. Using this new approach, we plot a few example GCC-PHATs for the SCPMA at different noise levels. The approach is applied to voice segments only of the existing speech recordings, which are obtained through the provided ground truth. As you could find that an underlying pattern is shared among all these subplots. After that, the traditional algorithm adds the GCC-PHAT of all microphone pairs together to calculate the SRP-PHAT, and the time delay that leads to the largest SRP-PHAT can be used to estimate the DOA. The conventional SRP-PHAT has been proved to be effective under low to medium interferences, whereas can the performance in highly cooperative environments be improved? In addition, the error of DOA estimation using SRP-PHAT is not predictable, which means there is no pattern in the error distribution. For the subarray-based signal processing, the SRP-PHAT also faces difficulties in calculating the overall power. An imperfect solution we proposed before can be seen at the bottom. Inspired by the strengths of learning of deep neural networks, this work tries to use deep learning to exploit the information underlying the GCC-PHAT and directly map the GCC-PHAT to estimated DOAs. The GCC-PHAT is formatted as two-dimensional images, and a 2D convolutional neural network is used to extract the features. The network structure of the CNN is shown in this slide, which uses 4 blocks to implement feature extraction. In each block, there are a few 2D convolutional layers, a max pooling layer, and a dropout layer. The number of channels of the 2D convolutional layers doubles that of the previous block. Each 2D convolutional layer is followed by a batch normalization layer, and the activation function of all 2D convolutional layers is chosen as rectified linear unit for modeling nonlinearity and mitigating overfitting. This type of multi-channel CNN structure with pooling layers have been shown to well represent high-level features of the input, and we utilize it to gradually look into GCC-PHAT from general DOA information to deeper ones, which is beneficial to make full use of features contained in GCC-PHAT. Conventionally, there are a few fully connected layers following these blocks to further extract features, but our experiments show that those are not necessary, as multiple layers of CNN already have excellent capabilities of feature representation, and the extra computational load involved by the fully connected layers is not desired in this work. So, at the last stage, we only have one fully connected layer, one softmax layer, and a classification layer to output final results. This proposed structure for speech DOA estimation using Coprime arrays is termed as Coprime net. By training Coprime net on a prepared dataset properly, the network output in the test phase will directly be the estimated DOA. Our experiment compares 3 types of microphone arrays with the same number of microphones and aperture, which are the SCPMA, CPMA, and ULA. As you can see in the top table, the 2 coprime arrangements possess much higher operating frequencies than that of the ULA, which means the coprime arrays are inclined to record less interferences. Recordings are simulated in a large room using an existing speech corpus, the IEEE corpus. The sampling frequency is 25 kHz, and the noise levels from 10 dB to 40 dB SNR as well as the no noise scenario are considered. Due to the room geometry, we only trained the sound source coming from 55 degree to 125 degree, with the source array distance being 7 meters. The resolution of the azimuth is 1 degree, so there are totally 71 DOA classes as the network output. The 3 ground truth DOAs are used for evaluations in the test phase. A time frequency analysis is conducted on 200 millisecond frames with a 50% overlap. The Coprime net was trained in MATLAB 2021A with an initial learning rate of 0.01, with all other details for training listed in this slide. The final accuracy in training for all the 3 microphone arrays are above 95%. The results show that the speech DOA estimation using the ULA, CPMA, and SCPMA are all accurate on their different levels of noise, which present the benefit of applying deep learning to estimate speech DOA in trained environments. For the highest noise scenario, the SCPMA leads to the highest accuracy, higher than that of the ULA by around 9% and 7% in terms of MAE and RMSE separately. This result evidences the advantage of the semi-coprime array geometry in resisting high noise, and the proposed GCC-PHAT formulation for coprime arrays successfully explores such advantages for robust speech DOA estimation. To further demonstrate the advantage of using the new GCC-PHAT for coprime arrays and also the deep learning approach, we compare this work with the previous SRP-PHAT using the traditional GCC-PHAT in our APSIPA 2019 paper. Although the simulation conditions of the 2 methods are mostly the same, a direct comparison of the accuracy cannot be made due to the difference in preparing data, including the frame length, frequency bit number of Fourier transform, azimuthal resolution, and whether the unvoiced segments and silence are removed. We instead compare distribution of errors under high noise for these 2 papers, as you can see in this slide. At a 10 dB SNR, the errors using deep learning for all 3 microphone arrays are concentrated, and the majority of errors have the same value. The SRP-PHAT leads to more variations than deep learning. For practical use, invariant errors are always preferable for the robustness of speech DOA estimation, which is an advantage of the proposed method over the SRP-PHAT approach. This paper makes 2 main changes to our APSIPA 2019 paper, which are the new GCC-PHAT for coprime arrays and the Coprime net for speech DOA estimation. Our conclusion is that deep learning further explores the strengths of coprime microphone arrays in suppressing interferences and speech DOA estimation. This finding has potential implications for a clear recording of sounds at broadband frequencies and the high robustness to interferences using the proposed approach, which will benefit its applications in teleconferencing systems, smart home devices, robotics, and autonomous vehicles. Thus, it has a bright prospect to contribute to our future smart lifestyles. Future work will simulate the speech recording in more complex acoustic environments, considering different levels of room reverberation and multiple speakers. The speech for testing will include the unvoiced segments and silence, which is the case in the real world. A broader range of DOAs will be investigated in more rooms with different geometries, and the Coprime net will be improved to further increase the performance of coprime microphone arrays. Okay, this is all I would like to present today. I hope you enjoy it, and I wish I could discuss research with you in person in the near future. Now, Please raise your questions and I'll be in the chat.